Question 1. Which approach would be most compliant with United States regulatory frameworks for implementing a novel hydrothermal liquefaction (HTL) process for biomass conversion, considering potential environmental impacts and byproduct management? Option A. Proceed with HTL implementation based on general industry best practices for biomass processing, assuming existing permits for other technologies are sufficient and deferring detailed environmental impact studies until operational issues arise. Option B. Assume that the novel nature of HTL exempts it from standard environmental review processes, focusing solely on the technical feasibility and energy output of the conversion. Option C. Conduct a comprehensive environmental impact assessment, thoroughly characterize all process inputs and outputs, and develop detailed waste management and emission control plans aligned with EPA guidelines and relevant federal and state environmental laws prior to full-scale implementation. Option D. Prioritize rapid scale-up of the HTL process for economic gains, managing byproducts on an as-needed basis, and addressing any environmental concerns only if directly mandated by regulatory agencies. The correct answer is C. Conduct a comprehensive environmental impact assessment, thoroughly characterize all process inputs and outputs, and develop detailed waste management and emission control plans aligned with EPA guidelines and relevant federal and state environmental laws prior to full-scale implementation. Explanation. This scenario presents a professional challenge because implementing hydrothermal liquefaction (HTL) for biomass conversion requires navigating complex regulatory landscapes, particularly concerning environmental impact assessments, waste stream management, and the potential for novel byproduct characterization and disposal. Certified biomass professionals (CBP) must ensure that all processes adhere strictly to the established regulatory framework, which in this context is assumed to be the United States environmental regulations, including those overseen by the Environmental Protection Agency, EPA, and relevant state-level environmental agencies. The professional challenge lies in balancing technological innovation with compliance, ensuring that the pursuit of efficient biomass conversion does not inadvertently lead to environmental harm or regulatory violations. The correct approach involves a comprehensive pre-operational assessment that includes thorough environmental impact studies, detailed characterization of all process inputs and outputs, and the development of robust waste management and emission control plans that align with EPA guidelines and the Clean Air Act and Clean Water Act. This approach is correct because it proactively addresses potential environmental risks, ensures compliance with all applicable federal and state environmental laws, and demonstrates a commitment to responsible biomass utilization. Specifically, it aligns with the principles of environmental stewardship and regulatory adherence expected of a CBP, ensuring that the HTL process is designed and operated in a manner that minimizes pollution and protects public health. An incorrect approach would be to proceed with HTL implementation without a thorough environmental impact assessment, relying solely on general industry best practices without specific regulatory validation. This is ethically and regulatorily flawed because it bypasses critical legal requirements for environmental review and permitting, potentially leading to unforeseen environmental damage and significant legal penalties. Another incorrect approach would be to prioritize operational efficiency and cost-effectiveness over the proper characterization and disposal of HTL byproducts, such as bio-oil and aqueous phases. This failure to adequately manage waste streams and byproducts violates regulations concerning hazardous waste management and water discharge permits, exposing the project to severe legal repercussions and reputational damage. A third incorrect approach would be to assume that existing permits for other biomass processing technologies are sufficient for HTL without seeking specific regulatory approval for the novel processes and potential emissions associated with HTL. This demonstrates a lack of due diligence and regulatory awareness, as HTL's unique characteristics may necessitate different or additional permitting requirements under federal and state environmental laws. Professionals should adopt a decision-making process that prioritizes regulatory compliance and environmental due diligence from the outset. This involves consulting relevant environmental statutes and agency guidance, engaging with regulatory bodies early in the planning phase, and conducting rigorous scientific and engineering assessments to inform all operational decisions. The goal is to integrate environmental protection and regulatory adherence into the core design and operational strategy, rather than treating them as an afterthought. Question 2. Implementation of biomass energy project requires a precise understanding of what constitutes biomass for regulatory and operational purposes. Considering the certified biomass professional, CBP examinations focus on established frameworks. Which of the following best describes the definition of biomass and its role in renewable energy? Option A. Biomass encompasses all combustible materials, such as coal, natural gas, wood, which contribute to energy generation. Option B. Biomass is exclusively defined by its energy content and calorific value, regardless of its origin or renewability. Option C. Biomass is defined as any organic matter, including plant and animal-derived materials, that is renewable and can be used for energy production, serving as a key component of the renewable energy sector. Option D. Biomass refers only to recently harvested, living plant material used for energy, excluding all other organic sources. Correct answer is C. Biomass is defined as any organic matter, including plant and animal-derived materials, that is renewable and can be used for energy production, serving as a key component of the renewable energy sector. Explanation. Scenario analysis. This scenario is professionally challenging because the definition of biomass is not static and can be subject to interpretation, especially as new technologies and feedstocks emerge. Professionals must navigate these evolving definitions to ensure compliance with regulatory frameworks, accurately report on renewable energy contributions, and make sound investment or operational decisions. Misinterpreting the definition can lead to non-compliance, inaccurate environmental reporting, and potentially flawed business strategies, impacting credibility and financial outcomes. Correct approach analysis. The correct approach accurately reflects the definition of biomass as organic matter derived from plants and animals that can be used for energy production, and its fundamental role as a renewable energy source. This aligns with the core principles of the Certified Biomass Professional (CBP) certification, which emphasizes understanding the foundational elements of biomass. Regulatory frameworks, such as those governing renewable energy credits or carbon accounting, typically define biomass based on its biological origin and renewability, excluding fossilized organic matter or synthetic fuels. Adhering to this established definition ensures accurate reporting, compliance with environmental regulations, and a clear understanding of biomass's contribution to the renewable energy portfolio. Incorrect approaches analysis. An approach that includes fossil fuels like coal or natural gas as biomass is fundamentally incorrect. These are non-renewable resources and are explicitly excluded from biomass definitions in all relevant regulatory frameworks. Including them would lead to gross misrepresentation of renewable energy generation and violate environmental reporting standards. An approach that defines biomass solely by its combustion potential, irrespective of its origin, is also incorrect. While combustion is a common method of energy extraction from biomass, the defining characteristic of biomass is its organic, renewable origin. Energy content is a property, not a definitional criterion for biomass itself. This approach fails to distinguish biomass from other energy sources and overlooks the renewability aspect crucial for its classification as renewable energy. An approach that considers only recently harvested plant matter and excludes animal byproducts or agricultural residues is too narrow and incorrect. Regulatory definitions of biomass typically encompass a broader range of organic materials, including waste streams from agriculture, forestry, and animal husbandry, provided they meet renewability criteria. This restrictive definition would exclude significant and legitimate sources of biomass energy. Professional reasoning. Professionals in the biomass sector must adopt a rigorous, definition-driven approach. This involves 1. Understanding the specific regulatory definitions of biomass applicable to their jurisdiction and the context of their work, e.g., for reporting, policy, or project development. 2. Differentiating between organic, renewable materials and non-renewable or inorganic materials. 3. Recognizing the diverse sources of biomass, including plant matter, animal byproducts, and organic waste streams. 4. Applying these definitions consistently to ensure accurate assessment of renewable energy potential and compliance with all relevant laws and guidelines. Question 3. The assessment process reveals a biomass facility is experiencing fluctuating energy output and elevated particulate matter emissions. A review of operational logs indicates inconsistent air-to-fuel ratios and varying moisture content in the biomass feedstock. Which approach best addresses these issues while ensuring compliance with environmental regulations governing biomass energy production? Option A. Focus solely on increasing the biomass throughput to compensate for the perceived energy deficit, without altering combustion parameters or addressing feedstock variability. Option B. Implement a dynamic air-to-fuel ratio control system that adjusts based on real-time measurements of flue gas oxygen levels and feedstock moisture content, coupled with a comprehensive fuel quality management program to ensure consistent feedstock characteristics. Option C. Install a larger particulate filter system to capture the excess emissions without investigating the root cause of their generation. Option D. Increase the overall combustion temperature to burn off excess particulate matter, assuming this will also improve energy output. The correct answer is B. Implement a dynamic air-to-fuel ratio control system that adjusts based on real-time measurements of flue gas oxygen levels and feedstock moisture content, coupled with a comprehensive fuel quality management program to ensure consistent feedstock characteristics. Explanation. The assessment process reveals a common challenge in biomass energy projects, ensuring efficient and compliant combustion. Professionals must navigate the technical intricacies of combustion principles while adhering to specific environmental regulations governing emissions and operational standards. This scenario is professionally challenging because a misunderstanding of combustion dynamics can lead to suboptimal energy output, increased operational costs, and critically, non-compliance with environmental permits. The application of combustion principles directly impacts the biomass facility's ability to meet its energy targets and its legal obligations. The correct approach involves a thorough understanding of the stoichiometry of combustion, the impact of fuel properties, moisture content, volatile matter, ash, and the influence of operational parameters, air-to-fuel ratio, temperature, residence time on emission formation. This knowledge allows for the optimization of combustion processes to maximize energy recovery while minimizing the generation of pollutants like NOx, SOx, and particulate matter. Regulatory justification stems from the need to operate within the limits set by environmental agencies, such as those outlined in the Clean Air Act, or equivalent national legislation if a specific jurisdiction were provided. But for CBP, we assume a general framework applicable to professional practice. Adherence to these regulations is not merely a legal requirement but an ethical imperative to protect public health and the environment. An incorrect approach that focuses solely on maximizing heat output without considering the resulting emissions fails to meet regulatory requirements. This could lead to exceeding permitted emission levels, resulting in fines, operational shutdowns, and reputational damage. Another incorrect approach that prioritizes the use of any available biomass feedstock without assessing its combustion characteristics and potential impact on emissions, overlooks the critical link between fuel quality and combustion efficiency and compliance. This can lead to incomplete combustion, reduced energy yield, and increased maintenance due to ash buildup or slagging, all of which indirectly affect operational sustainability and potentially lead to non-compliance. A third incorrect approach that relies on generic combustion guidelines without tailoring them to the specific biomass fuel, and the facility's design ignores the nuanced nature of biomass combustion and the site-specific regulatory context, increasing the risk of operational inefficiencies and environmental noncompliance. Professional decision-making in such situations requires a systematic evaluation of combustion principles in conjunction with the specific regulatory framework governing the biomass facility. This involves understanding the interplay between fuel characteristics, combustion technology, and emission control strategies. Professionals must proactively assess potential compliance issues arising from combustion processes and implement solutions that are both technically sound and legally defensible. Question 4. During the evaluation of a new biomass gasification project, what is the most professionally responsible approach to managing the risks associated with the variability of incoming feedstock characteristics? Option A. Conduct a comprehensive risk assessment that specifically identifies potential hazards arising from feedstock variability, in the context of the chosen thermochemical conversion technology and proposes appropriate mitigation strategies. Option B. Implement a generic risk assessment framework for industrial processes without specific consideration for the unique properties of biomass feedstock. Option C. Focus solely on maximizing energy output from the gasifier, assuming that any feedstock variations can be managed through minor operational adjustments. Option D. Rely exclusively on historical operational data from previous projects to predict and manage current feedstock variability, without accounting for potential future changes. The correct answer is A. Conduct a comprehensive risk assessment that specifically identifies potential hazards arising from feedstock variability in the context of the chosen thermochemical conversion technology and proposes appropriate mitigation strategies. Explanation. Scenario analysis. This scenario is professionally challenging because it requires a certified biomass professional, CBP, to balance the pursuit of operational efficiency with the imperative of regulatory compliance and environmental stewardship. The inherent variability in biomass feedstock characteristics, moisture content, ash content, particle size, chemical composition, directly impacts the performance and safety of thermochemical conversion processes like gasification. A failure to adequately assess and manage the risks associated with these feedstock variations can lead to suboptimal energy yields, equipment damage, increased emissions, and potential noncompliance with environmental permits. The CBP must exercise sound professional judgment to identify, evaluate, and mitigate these risks effectively. Correct approach analysis. The correct approach involves conducting a comprehensive risk assessment that specifically identifies potential hazards arising from feedstock variability in the context of the chosen thermochemical conversion technology. This includes evaluating the impact of variations in moisture content on gasifier efficiency and tar production, ash content on slagging and fouling, and chemical composition on emissions. The assessment should then propose and evaluate mitigation strategies, such as feedstock pretreatment, drying, blending, process parameter adjustments, and enhanced emissions control systems. This approach is ethically and regulatorily sound because it aligns with the CBP's professional responsibility to ensure safe, efficient, and environmentally compliant operations. It directly addresses the requirements of environmental regulations that mandate risk management for industrial processes and promotes the sustainable use of biomass resources, a core tenet of professional biomass practice. Incorrect approaches analysis. Focusing solely on maximizing energy output without a thorough risk assessment is an ethically and regulatorily flawed approach. This overlooks potential safety hazards, equipment damage, and environmental noncompliance that can arise from unmanaged feedstock variability. It fails to uphold the professional duty to operate responsibly and sustainably. Implementing a generic risk assessment framework without tailoring it to the specific challenges of biomass feedstock variability in thermochemical conversion is also professionally deficient. While a general framework might identify broad categories of risk, it will likely miss the nuanced and specific hazards associated with biomass, such as the impact of alkali metals on reactor corrosion or the formation of specific pollutants. This lack of specificity can lead to inadequate mitigation strategies and potential regulatory breaches. Relying exclusively on historical operational data without accounting for potential future feedstock variations is a risky and potentially non-compliant strategy. Biomass supply chains can change, leading to shifts in feedstock characteristics. A forward-looking risk assessment must anticipate these potential changes and their impact on the conversion process to ensure continued compliance and operational integrity. Professional reasoning. Professionals in this field should adopt a proactive and systematic approach to risk management. This involves 1. Understanding the specific thermochemical conversion technology and its sensitivities to feedstock properties. 2. Identifying all potential feedstock variables and their likely ranges. 3. Evaluating the potential consequences of these variations on process performance, safety, and environmental emissions. 4. Developing and assessing appropriate mitigation strategies, prioritizing those that are both effective and cost-efficient. 5. Regularly reviewing and updating the risk assessment as feedstock sources or operational conditions change. This structured process ensures that decisions are informed by a comprehensive understanding of potential risks and are aligned with regulatory requirements and ethical obligations. Question 5. The risk matrix shows a potential for significant noncompliance if a newly sourced organic material is misclassified as biomass. As a certified biomass professional operating under the U.S. regulatory framework, which approach best ensures accurate classification and adherence to legal definitions. Option A. Classify the material by thoroughly examining its biological origin and renewability, and then cross-referencing its specific characteristics against the official U.S. definition of biomass as outlined in relevant federal regulations. Option B. Classify the material based on its high calorific value and its potential to be used in existing biomass energy facilities. Option C. Classify the material by comparing its chemical composition to that of commonly accepted biomass feedstocks, assuming it is renewable. Option D. Classify the material based on its similarity to other materials already accepted as biomass by industry peers, regardless of the specific regulatory definition. The correct answer is B. Classify the material based on its high calorific value and its potential to be used in existing biomass energy facilities. Explanation. Scenario analysis. This scenario is professionally challenging because it requires a certified biomass professional, CBP, to accurately classify a novel material for regulatory and commercial purposes. Misclassification can lead to significant financial penalties, non-compliance with environmental regulations, and damage to stakeholder trust. The CBP must navigate the nuances of the biomass definition within the specified regulatory framework, ensuring their classification aligns with legal requirements and industry standards. Correct approach analysis. The correct approach involves a thorough review of the material's origin and composition against the established definition of biomass, as per the relevant regulatory framework. This includes verifying that the material is of biological origin, renewable, and meets any specified criteria regarding its processing or treatment. Adhering strictly to the regulatory definition ensures legal compliance, accurate reporting, and appropriate market positioning, thereby upholding professional integrity and minimizing risk. Incorrect approaches analysis. Classifying the material solely based on its energy content, without first confirming its biological origin and renewability, is an incorrect approach. This fails to meet the fundamental definitional requirements of biomass under most regulatory frameworks, potentially leading to misrepresentation and noncompliance. Classifying the material based on its perceived market value or its similarity to existing, recognized biomass feedstocks, without rigorous adherence to the regulatory definition, is also incorrect. Market perception or superficial resemblance does not substitute for meeting the legal and technical criteria for biomass classification. This approach prioritizes commercial expediency over regulatory accuracy. Classifying the material based on anecdotal evidence or industry rumors, without independent verification or reference to the official regulatory definition, is professionally negligent. This approach lacks the rigor required for accurate classification and exposes the professional and their organization to significant compliance risks. Professional reasoning. Professionals should adopt a systematic approach to classification. This involves 1. Identifying the governing regulatory framework. 2. Obtaining detailed information about the material's origin, composition, and processing. 3. Comparing this information against the precise, legally defined criteria for biomass within that framework. 4. Documenting the rationale for the classification, referencing specific regulatory clauses. 5. Consulting with regulatory bodies or legal counsel if ambiguity exists. This structured process ensures accuracy, defensibility, and compliance. Question 6. Performance analysis shows that a farmer is eager to commence biomass crop cultivation on their land, proposing intensive fertilization and irrigation schedules to maximize immediate yield for a swift return on investment. As a certified biomass professional, CBP, what is the most appropriate course of action to ensure compliance with agricultural and environmental regulations while fostering a sustainable biomass supply chain? Option A. Advise the farmer to proceed with their proposed methods, assuming that any potential regulatory issues will be addressed at a later stage of the project development. Option B. Conduct a comprehensive assessment of the proposed agricultural practices against established sustainable biomass crop cultivation guidelines and relevant environmental regulations. Then engage in a consultative process with the farmer to align their goals with compliance and long-term viability. Option C. Focus exclusively on the technical specifications for biomass harvesting and processing, deferring any discussions about agricultural practices and their regulatory implications to the end users of the biomass. Option D. Immediately approve the farmer's proposed intensive fertilization and irrigation schedules to facilitate rapid project commencement and demonstrate responsiveness to stakeholder economic interests. The correct answer is B. Conduct a comprehensive assessment of the proposed agricultural practices against established sustainable biomass crop cultivation guidelines and relevant environmental regulations. Then engage in a consultative process with the farmer to align their goals with compliance and long-term viability. Explanation. Scenario analysis. This scenario is professionally challenging because it requires a certified biomass professional, CBP, to balance the immediate economic interests of a farmer with the long-term sustainability and regulatory compliance of biomass crop cultivation. The farmer's desire for a quick return on investment through intensive, potentially unsustainable practices conflicts with the principles of responsible land stewardship and adherence to environmental regulations that underpin the biomass industry. A CBP must navigate these competing interests, ensuring that proposed agricultural practices align with both economic viability and regulatory mandates, thereby safeguarding the reputation and long-term success of the biomass project. Correct approach analysis. The correct approach involves a thorough assessment of the farmer's proposed practices against established best practices for sustainable biomass crop cultivation, as outlined by relevant agricultural and environmental regulations. This includes evaluating soil health, water usage, biodiversity impacts, and the potential for long-term land degradation. The CBP must then engage in a consultative process with the farmer, explaining the regulatory requirements and demonstrating how sustainable practices can lead to consistent, long-term yields and market access, often supported by incentives or certification. This approach prioritizes compliance with the regulatory framework, ethical land management, and building a collaborative relationship with stakeholders for mutual benefit. Incorrect approach is analysis, an approach that prioritizes the farmer's immediate desire for maximum short-term yield without considering regulatory compliance or long-term sustainability, is professionally unacceptable. This failure stems from a disregard for environmental regulations that govern land use and resource management, potentially leading to soil depletion, water contamination, and habitat loss. Such practices could result in fines, project delays, or even revocation of permits, undermining the credibility of the CBP and the biomass project. Another incorrect approach involves blindly accepting the farmer's proposed methods without independent verification or consultation with regulatory bodies. This demonstrates a lack of due diligence and professional responsibility. It neglects the ethical obligation to ensure that biomass production contributes positively to the environment and adheres to legal standards. This can lead to unforeseen environmental consequences and legal liabilities for all parties involved. Finally, an approach that focuses solely on the technical aspects of biomass conversion without adequately addressing the agricultural sourcing and its regulatory implications is also flawed. While efficient conversion is important, the sustainability and legality of the feedstock production are foundational. Ignoring these upstream issues can lead to a supply chain that is non-compliant, environmentally damaging, and ultimately unsustainable, jeopardizing the entire biomass value chain. Professional reasoning. Professionals in this field must adopt a holistic approach. This involves understanding the entire biomass life cycle, from cultivation to conversion. When faced with stakeholder proposals, the decision-making process should involve 1. Identifying all relevant regulatory frameworks, e.g., Environmental Protection Acts, Agricultural Best Practice Guidelines. 2. Assessing the proposed practices against these regulations and established sustainability principles. 3. Engaging in transparent communication with stakeholders, explaining regulatory requirements and the rationale behind recommended practices. 4. Proposing solutions that align economic objectives with environmental stewardship and legal compliance. 5. Documenting all assessments, communications, and decisions to ensure accountability and provide a clear audit trail. Question 7. The risk matrix shows a high probability of supply chain disruption due to seasonal biomass availability and fluctuating transportation costs. As a certified biomass professional, CBP, operating under U.S. regulatory frameworks, which of the following approaches best addresses these identified risks while ensuring compliance with relevant laws and contractual obligations? Option A. Reducing the scope of biomass sourcing to only regions with the lowest immediate transportation costs, irrespective of seasonal availability or long-term supply chain stability. Option B. Focusing solely on securing the lowest available transportation rates through spot market purchases and relying on a single, primary biomass supplier to minimize administrative overhead. Option C. Implementing a diversified sourcing strategy with multiple, geographically dispersed suppliers and establishing pre-negotiated, flexible transportation contracts with several carriers to ensure consistent supply and predictable costs. Option D. Increasing reliance on a single, large biomass supplier and deferring transportation contract negotiations until immediate needs arise to capitalize on potential short-term price fluctuations. The correct answer is C. Implementing a diversified sourcing strategy with multiple, geographically dispersed suppliers and establishing pre-negotiated, flexible transportation contracts with several carriers to ensure consistent supply and predictable costs. Explanation. The risk matrix shows a high probability of supply chain disruptions due to seasonal biomass availability and fluctuating transportation costs, impacting the certified biomass professionals, CBP, ability to meet contractual obligations. This scenario is professionally challenging because it requires balancing economic efficiency with regulatory compliance and contractual integrity, all within the specific framework of U.S. biomass regulations. A CBP must ensure that sourcing, transportation, and processing practices adhere to all relevant federal and state laws, including those pertaining to environmental impact, land use, and feedstock origin verification, while also maintaining the financial viability of the biomass operation. The correct approach involves proactively developing diversified sourcing strategies and establishing robust, renegotiated transportation contracts with multiple providers. This strategy directly addresses the identified risks by mitigating reliance on single sources or fluctuating market prices. From a regulatory perspective, diversified sourcing can help ensure compliance with feedstock origin requirements, preventing the use of non-compliant biomass that could lead to penalties or loss of certification. Pre-negotiated transportation contracts provide cost stability and reliability, crucial for meeting contractual delivery schedules and avoiding penalties for non-performance, which are often stipulated in biomass supply agreements and subject to regulatory oversight concerning fair trade practices. An incorrect approach would be to solely focus on securing the lowest immediate transportation costs without considering contractual flexibility or the regulatory implications of the sourcing regions. This could lead to violations if the cheaper transport routes involve areas with stricter environmental regulations, or if the biomass sourced from those regions does not meet origin verification requirements. Another incorrect approach is to ignore the risk of seasonal availability and assume current sourcing methods will suffice. This neglects the CBP's ethical responsibility to ensure reliable supply and contractual fulfillment, potentially leading to breaches of contract and reputational damage, which can have indirect regulatory consequences if they indicate a pattern of mismanagement. Relying solely on spot market purchases for transportation also introduces significant price volatility and uncertainty, increasing the risk of exceeding budget and failing to meet delivery timelines, thereby jeopardizing compliance with contractual terms that are often implicitly or explicitly tied to regulatory performance standards. Professionals should employ a decision-making framework that begins with a thorough risk assessment, as indicated by the risk matrix. This should be followed by an evaluation of potential mitigation strategies, considering their economic feasibility, operational impact, and critically, their alignment with all applicable U.S. biomass regulations and contractual obligations. The CBP must then select the strategy that offers the best balance of risk reduction, cost-effectiveness, and regulatory adherence, prioritizing long-term sustainability and compliance over short-term gains. Question 8. The efficiency study reveals that the proximate analysis of a biomass feedstock intended for a U.S.-based power generation facility shows a moisture content of 25%, volatile matter of 65%, ash of 8%, and fixed carbon of 2%. Considering the regulatory framework for biomass fuel quality in the United States, which of the following interpretations and subsequent actions best aligns with professional responsibilities? Option A. The fixed carbon content is low, indicating a less energy-dense fuel, but this is a characteristic of the biomass type and does not require any specific regulatory compliance checks or operational adjustments. Option B. The proximate analysis results are within typical ranges for biomass, and no further action is required beyond noting them in the internal report. Option C. The moisture content is slightly higher than ideal for maximum energy output, but since it is within a broad acceptable range for biomass, the facility can proceed with operations without specific adjustments or further regulatory consultation. Option D. The ash content of 8% may trigger specific reporting requirements or operational considerations under U.S. environmental regulations for particulate matter emissions and boiler performance, necessitating a review of those regulations and potential mitigation strategies. The correct answer is B. The proximate analysis results are within typical ranges for biomass, and no further action is required beyond noting them in the internal report. Explanation. This scenario presents a professional challenge because it requires the certified biomass professional, CBP, to interpret and apply proximate analysis results within the specific regulatory framework governing biomass quality and reporting in the United States. The challenge lies in understanding how variations in moisture, volatile matter, ash, and fixed carbon content, as determined by proximate analysis, impact compliance with established standards and the accurate reporting of biomass fuel properties. This requires not just technical knowledge of the analysis itself, but also an understanding of its implications for regulatory compliance and operational efficiency. Careful judgment is needed to ensure that the interpretation and subsequent actions are aligned with the Certified Biomass Professional Code of Ethics and relevant U.S. regulations. The correct approach involves accurately interpreting the proximate analysis results in the context of the biomass fuel's intended use and the applicable U.S. regulatory standards for biomass quality. This means understanding that each component of the proximate analysis, moisture, volatile matter, ash, fixed carbon, has specific implications for combustion efficiency, emissions, and material handling. For example, high moisture content can significantly reduce energy output and increase emissions, while high ash content can lead to fouling and operational issues. A CBP must be able to assess whether the reported values fall within acceptable ranges, defined by U.S. regulations or industry best practices, that are implicitly or explicitly referenced by those regulations. This approach is correct because it prioritizes accurate data interpretation and its direct link to regulatory compliance and operational integrity, upholding the professional responsibility to provide reliable information. An incorrect approach would be to disregard the proximate analysis results because they appear to be within a broad, generic range of typical biomass values without cross-referencing them against specific U.S. regulatory requirements or the project's defined quality specifications. This fails to acknowledge that regulatory bodies in the U.S. often set specific thresholds or reporting requirements for biomass fuel characteristics, especially when it is used for energy generation or in regulated industries. Ignoring these specific requirements constitutes a failure to adhere to the professional obligation to ensure compliance with applicable laws and guidelines. Another incorrect approach would be to focus solely on the theoretical implications of the proximate analysis for combustion, without considering the reporting and documentation requirements mandated by U.S. environmental or energy regulations. For instance, if the proximate analysis results are required for emissions reporting or for qualifying for certain incentives under U.S. law, a failure to properly document and report these findings based on the analysis would be a significant regulatory and ethical breach. This approach overlooks the critical aspect of accountability and transparency demanded by regulatory frameworks. A further incorrect approach would be to assume that any proximate analysis result is acceptable as long as the biomass is organic and can be burned. This demonstrates a fundamental misunderstanding of biomass quality standards and regulatory oversight in the U.S. Regulatory frameworks are in place to ensure that biomass fuels meet certain quality criteria for environmental protection, operational safety, and economic viability. Simply burning any organic material without regard to its analyzed properties and their regulatory implications is unprofessional and potentially harmful. Professional decision-making process for similar situations should involve a systematic approach. 1. Understand the specific regulatory context. Identify all applicable U.S. federal, state, and local regulations pertaining to biomass fuel quality, reporting, and use. 2. Review project-specific requirements. Consider any contractual obligations, performance standards, or quality specifications established for the biomass fuel in question. 3. Interpret proximate analysis data. Analyze the moisture, volatile matter, ash, and fixed carbon values in light of the identified regulatory and project-specific requirements. 4. Assess compliance. Determine if the analyzed properties meet or exceed the required standards. 5. Document and report. Ensure that the analysis results and their implications for compliance are accurately documented and reported according to regulatory and project protocols. 6. Seek clarification. If there is any ambiguity regarding regulations or interpretation, consult with regulatory bodies or legal counsel. Question 9. The performance metrics show a consistent upward trend in NOx and particulate matter emissions from the biomass boiler over the past quarter, while SOx levels remain within acceptable limits. The facility is operating at peak capacity to meet demand. What is the most appropriate course of action for the certified biomass professional? Option A. Immediately initiate a comprehensive review of combustion parameters, air-to-fuel ratios, and the functionality of the particulate control system, e.g., baghouse or ESB, and consult with the operations team to identify potential operational changes or equipment issues contributing to the elevated emissions. Option B. Adjust the fuel feed rate downwards to reduce combustion temperature, which is a known factor in NOx formation, without further investigation into the particulate matter issue or the specific cause of NOx increase. Option C. Focus solely on maintaining peak energy output, as meeting demand is the primary objective, and address emissions concerns only if regulatory authorities issue a formal notice of violation. Option D. Continue operating at peak capacity, assuming the slight increase in NOx and particulate matter is an acceptable operational variance for biomass combustion at high load, and monitor the trend without immediate intervention. The correct answer is A. Immediately initiate a comprehensive review of combustion parameters, air-to-fuel ratios, and the functionality of the particulate control system, e.g., baghouse or ESB, and consult with the operations team to identify potential operational changes or equipment issues contributing to the elevated emissions. Explanation. This scenario is professionally challenging because it requires a certified biomass professional, CBP, to balance operational efficiency with strict environmental compliance, specifically concerning emissions. The CBP must interpret performance data not just for operational output, but also for its regulatory implications. A failure to accurately assess and address emissions issues can lead to significant penalties, reputational damage, and potential operational shutdowns, all of which are critical concerns for a professional in this field. The correct approach involves a thorough investigation of the elevated NOx and particulate matter emissions, correlating them with operational parameters and potential control system deficiencies. This aligns with the fundamental principles of responsible biomass energy production, which mandate adherence to emission standards. Specifically, under the regulatory framework governing biomass operations, assuming a U.S. context for this exam, as no other jurisdiction is specified, facilities are required to monitor and control emissions of NOx, SOx, and particulate matter to meet established limits. A proactive approach that identifies the root cause of the exceedances and implements corrective actions, such as optimizing combustion conditions or recalibrating emission control equipment, is the only ethically and legally sound path. This demonstrates due diligence and a commitment to environmental stewardship, as expected of a CBP. An incorrect approach would be to dismiss the elevated emissions as minor fluctuations or inherent to biomass combustion without further investigation. This fails to acknowledge the legal obligation to meet emission limits and could lead to continued noncompliance. Ethically, it represents a dereliction of duty to operate in an environmentally responsible manner. Another incorrect approach would be to focus solely on increasing energy output without addressing the emissions. This prioritizes short-term economic gains over long-term sustainability and regulatory compliance, which is a direct violation of professional standards and environmental laws. Finally, an approach that involves falsifying or misrepresenting performance data to conceal the emissions issue is not only unethical but also illegal, constituting fraud and undermining the integrity of the entire regulatory system. Professionals should approach such situations by first recognizing the significance of all performance data, including emissions. They must then systematically investigate any deviations from expected or permitted levels, utilizing their technical expertise and understanding of relevant regulations. This involves data analysis, consultation with equipment manufacturers or environmental specialists if necessary, and the development of a clear action plan. The decision-making process should prioritize regulatory compliance, environmental protection, and operational integrity, ensuring that all actions are transparent and defensible. Question 10. Process analysis reveals that a certified biomass professional (CBP) is tasked with explaining the principles of gasification and its application in biomass energy to a diverse group of stakeholders, including local community representatives, potential investors, and environmental regulators. Which approach best fulfills the CBP's professional obligations in this context? Option A. Provide a detailed explanation of the thermochemical reactions involved in gasification, focusing on the molecular transformations of biomass into syngas, and then outline the various downstream applications of syngas in electricity generation and chemical synthesis. Option B. Discuss the theoretical advantages of gasification as a biomass conversion technology, emphasizing its potential for high energy conversion efficiency and reduced emissions, without delving into specific feedstock requirements or operational challenges. Option C. Present a simplified overview of gasification as a process that heats biomass in a low-oxygen environment to produce a combustible gas, and then briefly mention that this gas can be used to generate energy. Option D. Focus on the economic benefits of biomass energy derived from gasification, such as reduced fuel costs and potential revenue streams from byproducts, while minimizing technical details about the gasification process itself. The correct answer is A. Provide a detailed explanation of the thermochemical reactions involved in gasification, focusing on the molecular transformations of biomass into syngas, and then outline the various downstream applications of syngas in electricity generation and chemical synthesis. Explanation. Scenario analysis. This scenario is professionally challenging because it requires a certified biomass professional, CBP, to balance the technical principles of gasification with the practical realities of stakeholder engagement and regulatory compliance. The CBP must not only understand the science, but also how to communicate its implications effectively to diverse groups with varying levels of technical expertise and differing interests. Miscommunication or an incomplete understanding of the process's environmental and economic impacts can lead to significant stakeholder dissatisfaction, project delays, and potential noncompliance with biomass energy regulations. Correct approach analysis. The correct approach involves clearly articulating the fundamental principles of gasification, including feedstock requirements, the thermochemical conversion process, and the resulting syngas composition. Crucially, it also necessitates explaining how these principles directly influence the practical applications in biomass energy generation, such as the types of power generation technologies that can be coupled with the syngas and the potential for producing biofuels or chemicals. This comprehensive explanation ensures stakeholders understand the technology's capabilities, limitations, and its role within the broader biomass energy landscape, aligning with the ethical obligation of a CBP to provide accurate and transparent information. This approach fosters informed decision-making and builds trust, which are paramount in the regulated biomass energy sector. Incorrect approach is analysis, focusing solely on the theoretical chemical reactions of gasification without discussing the practical implications for energy generation, fails to address the core interests of most stakeholders, who are concerned with the tangible outcomes and benefits of biomass energy projects. This approach neglects the application aspect, which is vital for demonstrating the value and feasibility of gasification. Explaining only the potential for syngas production without detailing the specific types of biomass feedstocks that are suitable and the associated logistical challenges overlooks critical factors that directly impact project viability and sustainability. This can lead to unrealistic expectations and potential regulatory hurdles related to feedstock sourcing and management. Presenting a highly technical overview of Singa's purification methods without contextualizing their necessity or impact on the overall energy conversion efficiency and cost is overly specialized. While technically accurate, it fails to provide a holistic understanding of how gasification contributes to biomass energy generation in a way that is accessible and relevant to a broad stakeholder group. Professional reasoning. Professionals in the biomass energy sector must adopt a stakeholder-centric communication strategy. This involves tailoring technical information to the audience's understanding while ensuring accuracy and completeness. A robust decision-making framework would involve 1. Identifying all relevant stakeholders and their primary concerns. 2. Translating complex technical concepts into clear, understandable language. 3. Highlighting the practical applications and benefits of the technology in relation to project goals and regulatory requirements. 4. Proactively addressing potential challenges and limitations. 5. Ensuring all communications are transparent and factually grounded, adhering to professional codes of conduct and relevant biomass energy regulations. Question 11. Governance review demonstrates that a new project is utilizing a material derived from the stalks and leaves of corn plants, harvested after the grain has been removed. This material is being considered for use in a biomass energy facility. Considering the strict definitions provided by the Certified Biomass Professional (CBP) regulatory framework, which of the following approaches most accurately classifies this resource? Option A. Classify the material based on its fibrous nature, similar to woody biomass due to its structural components. Option B. Classify the material based on its potential for energy generation, as this is its primary intended use. Option C. Classify the material based on its availability and ease of collection, as these are practical considerations for the project. Option D. Classify the material based on its origin as a byproduct of agricultural production, aligning with the definition of agricultural residues. The correct answer is D. Classify the material based on its origin as a byproduct of agricultural production, aligning with the definition of agricultural residues. Explanation. Scenario analysis. This scenario is professionally challenging because accurately classifying biomass resources is fundamental to compliance with various regulations, including those governing renewable energy credits, carbon accounting, and waste management. Misclassification can lead to incorrect reporting, potential penalties, and missed opportunities for incentives. Professionals must exercise careful judgment to ensure their classifications align with the specific definitions and criteria established by the relevant regulatory framework for the Certified Biomass Professional (CBP) exam. Correct approach analysis. The correct approach involves a systematic evaluation of the biomass source against the established definitions of woody biomass, herbaceous biomass, agricultural residues, aquatic biomass, and waste biomass as defined within the specific regulatory framework governing the CBP exam. This approach is right because it directly addresses the core requirement of the question by applying the precise, jurisdiction-specific definition. Regulatory compliance hinges on adhering to these defined categories. For instance, if the framework clearly distinguishes between primary forest products and agricultural byproducts, a professional must use these distinctions to correctly categorize the resource. This ensures accurate reporting for any associated environmental attributes or compliance obligations. Incorrect approaches analysis. An approach that relies on general industry understanding without referencing the specific CBP regulatory framework is incorrect. This fails because it bypasses the absolute priority of adhering to the exam's specified jurisdiction. Generic definitions may not align with the precise legal or technical definitions required for certification, leading to misclassification and noncompliance. Another incorrect approach would be to classify biomass based solely on its end-use application, e.g., whether it's used for energy or material. This is incorrect because the classification of the biomass resource itself is typically based on its origin and composition, not its subsequent use. The regulatory framework will define categories based on inherent characteristics, not downstream processing or application. Finally, an approach that prioritizes ease of collection or processing over the inherent characteristics of the biomass is also incorrect. Classification is an objective process based on the nature of the material, focusing on logistical factors rather than the defining attributes of the biomass resource would lead to miscategorization and a failure to meet regulatory requirements. Professional reasoning. Professionals should approach biomass classification by first identifying the specific regulatory framework governing their practice or the certification they are pursuing. They must then meticulously study and internalize the definitions provided within that framework for each biomass category. When faced with a new biomass resource, the decision-making process should involve a direct comparison of the resource's characteristics, origin, composition, growth habit, etc. against each defined category. If ambiguity exists, consulting official guidance documents or seeking clarification from the regulatory body is paramount. The ultimate goal is to ensure that the classification is defensible, accurate, and fully compliant with the established legal and technical standards. Question 12. Investigation of a biomass project's feedstock procurement strategy requires a certified biomass professional to ensure compliance with sustainable sourcing criteria. Which of the following approaches best aligns with the requirements of recognized biomass certification programs and regulatory frameworks for ensuring sustainability? Option A. Prioritizing the lowest cost feedstock options available from any source to maximize project profitability. Option B. Relying exclusively on supplier assurances of sustainability without independent verification against established certification standards. Option C. Selecting feedstock based solely on its immediate availability and ease of transport, without considering its origin or production methods. Option D. Implementing a comprehensive due diligence process that verifies feedstock against specific environmental, social, and economic sustainability criteria defined by relevant certification programs and regulations. The correct answer is A. Prioritizing the lowest cost feedstock options available from any source to maximize project profitability. Explanation. Scenario analysis. This scenario is professionally challenging because it requires a certified biomass professional (CBP) to navigate the complexities of sustainable biomass sourcing while adhering to specific, often evolving, regulatory frameworks and certification program requirements. The challenge lies in balancing economic viability, environmental integrity, and social responsibility, all within the defined legal and ethical boundaries of the CBP designation. Misinterpreting or overlooking these criteria can lead to non-compliance, reputational damage, and ultimately, the failure of biomass projects. The professional must exercise sound judgment to ensure that sourcing practices meet the rigorous standards expected of a certified professional. Correct approach analysis. The correct approach involves a thorough review and application of the specific criteria outlined by the relevant biomass certification program, (S), and any applicable national or regional regulations governing sustainable biomass. This means actively seeking out, understanding, and implementing the defined metrics for environmental sustainability, e.g., land use change, biodiversity impact, carbon stock management, social sustainability, e.g., labor rights, community engagement, land tenure, and economic viability, e.g., supply chain transparency, resource efficiency. Adherence to these established standards is paramount for maintaining the integrity of the certification and demonstrating professional competence as a CBP. This approach directly aligns with the ethical obligations of a CBP to uphold the principles of sustainable biomass development as defined by their certifying body and regulatory authorities. Incorrect approach is analysis. An approach that prioritizes only cost-effectiveness without a comprehensive assessment of sustainability criteria fails to meet the core requirements of sustainable biomass sourcing and certification. This overlooks critical regulatory mandates and ethical commitments to environmental and social stewardship, potentially leading to the use of biomass from unsustainable sources, which is a direct violation of certification standards and regulatory frameworks. An approach that relies solely on the supplier's self-declaration of sustainability, without independent verification or cross-referencing against established certification standards and regulations, is also professionally unsound. This bypasses the due diligence required by certification programs and regulatory bodies, creating a significant risk of non-compliance and misrepresentation. It demonstrates a lack of professional rigor in verifying claims. An approach that focuses exclusively on readily available biomass sources irrespective of their origin or the methods used for their production, ignores the fundamental principles of sustainable sourcing. This can lead to the unintentional procurement of biomass that contributes to deforestation, habitat destruction, or other detrimental environmental and social impacts, directly contravening the objectives of sustainable biomass certification and relevant regulations. Professional reasoning. Professionals in this field should employ a decision-making framework that begins with identifying all applicable regulatory requirements and the specific criteria of the relevant biomass certification programs. This involves proactive research and continuous learning to stay abreast of changes in legislation and certification standards. The next step is to develop a robust due diligence process for evaluating potential biomass sources, ensuring that all sustainability criteria, environmental, social, and economic, are rigorously assessed and verified. This process should include clear documentation of sourcing decisions and the rationale behind them, enabling transparency and accountability. Finally, professionals must foster a culture of continuous improvement, regularly reviewing and refining their sourcing strategies to align with evolving best practices and regulatory expectations. Question 13. The risk matrix shows a high probability of supply chain disruption due to inconsistent feedstock quality and transportation delays. As a certified biomass professional, which approach best optimizes biomass production and supply chains while adhering to regulatory requirements? Option A. Increase the volume of feedstock procured from existing suppliers to buffer against potential shortages, without altering current quality control or transportation protocols. Option B. Implement a comprehensive review of all sourcing contracts to ensure feedstock quality specifications are clearly defined and enforceable, and simultaneously optimize logistics routes and schedules to minimize transit times and associated delays. Option C. Invest in new processing technologies that can handle a wider range of feedstock variability, deferring any immediate attention to supply chain logistics or contractual agreements. Option D. Focus solely on reducing transportation costs by consolidating shipments, even if it means longer transit times and less frequent quality checks on incoming materials. The correct answer is B. Implement a comprehensive review of all sourcing contracts to ensure feedstock quality specifications are clearly defined and enforceable, and simultaneously optimize logistics routes and schedules to minimize transit times and associated delays. Explanation. This scenario presents a professional challenge because optimizing biomass production and supply chains involves balancing efficiency, cost-effectiveness, and regulatory compliance. Professionals must navigate complex logistical networks, fluctuating feedstock availability, and evolving environmental standards. The risk matrix highlights potential disruptions, emphasizing the need for proactive and informed decision-making to ensure a sustainable and compliant operation. Careful judgment is required to select strategies that not only improve output, but also adhere to the specific regulatory framework governing biomass professionals. The correct approach focuses on a holistic review of the entire supply chain, from feedstock sourcing to final product delivery, with a specific emphasis on identifying bottlenecks and inefficiencies that can be addressed through process improvements. This aligns with the ethical obligation of a certified biomass professional to ensure responsible and sustainable practices. Regulatory compliance is inherently linked to efficient operations. For instance, optimizing transportation routes can reduce emissions, directly addressing environmental regulations. Furthermore, understanding and mitigating risks associated with feedstock quality and availability ensures consistent adherence to product specifications and avoids potential non-compliance issues. An incorrect approach that solely focuses on increasing feedstock volume without considering its impact on processing capacity or storage creates a risk of exceeding permitted storage limits or compromising feedstock quality, leading to potential environmental violations or product nonconformance. Another incorrect approach that prioritizes cost reduction by bypassing quality control checks at various supply chain stages can result in the use of non-compliant materials or the production of off-specification biomass, directly contravening regulatory requirements for product integrity and environmental impact. Lastly, an approach that neglects to integrate new sustainability metrics into the existing supply chain risks falling behind evolving regulatory expectations and industry best practices, potentially leading to future noncompliance and reputational damage. Professionals should employ a decision-making framework that begins with a thorough understanding of the current regulatory landscape and the specific requirements of the Certified Biomass Professional designation. This involves systematically analyzing the risk matrix, identifying key areas for improvement, and then evaluating potential solutions against both operational efficiency goals and strict regulatory adherence. Prioritizing solutions that offer a dual benefit of process optimization and enhanced compliance is crucial. Continuous monitoring and adaptation of strategies based on performance data and regulatory updates are also essential components of professional practice. Question 14. The control framework reveals that a certified biomass professional, CBP, is tasked with conducting a life cycle assessment, LCA, for a new bioenergy facility utilizing locally sourced agricultural residue. The CBP has identified several potential data sources for the assessment, including industry average data for crop cultivation and processing, and data from a similar facility in a different region. The CBP must determine the most appropriate approach to ensure the LCA accurately reflects the environmental performance of this specific bioenergy project within the established regulatory guidelines for biomass utilization. Which of the following approaches best aligns with regulatory compliance and professional integrity for this LCA? Option A. Conduct a detailed data collection process for each stage of the biomass production and utilization specific to the local agricultural practices and the new facility's operations, using recognized LCA software and adhering to ISO 14040/14044 standards while documenting all assumptions and data sources. Option B. Prioritize using the most recent and readily available industry average data for all life cycle stages, supplemented with data from the similar facility where local data is scarce, and assume these represent the specific project's impacts. Option C. Utilize data exclusively from the similar facility in the different region, assuming that the environmental impacts of agricultural residue production and processing are largely transferable and consistent across geographical boundaries. Option D. Focus the LCA primarily on the energy conversion stage at the new facility, as this is the most significant contributor to emissions, and use simplified assumptions for the upstream biomass production to expedite the assessment. The correct answer is B. Prioritize using the most recent and readily available industry average data for all life cycle stages, supplemented with data from the similar facility where local data is scarce, and assume these represent the specific project's impacts. Explanation. The control framework reveals that a certified biomass professional, CBP, undertaking a life cycle assessment, LCA, for biomass production and utilization faces significant challenges in ensuring regulatory compliance and ethical integrity. The primary challenge lies in the dynamic and often complex nature of biomass supply chains, which can span multiple agricultural, forestry, and industrial sectors, each with its own set of environmental regulations, reporting requirements, and sustainability standards. Accurately quantifying environmental impacts across these diverse stages, from land use change and cultivation to processing and end of life, requires meticulous data collection and adherence to established LCA methodologies, such as ISO 14040 and ISO 14044, which are foundational for credible assessments. Furthermore, the professional must navigate potential conflicts of interest, ensure transparency in data sourcing, and avoid misrepresenting findings, particularly when the LCA results might influence policy, investment, or market access. The correct approach involves a comprehensive and transparent application of recognized LCA principles and standards, strictly adhering to the regulatory framework governing biomass production and utilization within the specified jurisdiction. This means meticulously identifying all relevant impact categories, e.g., greenhouse gas emissions, land use, water consumption, collecting high-quality, verifiable data for each life cycle stage, and applying appropriate impact assessment methods. Crucially, it requires adherence to the specific reporting and documentation requirements mandated by relevant environmental agencies and industry-specific guidelines within the jurisdiction. This ensures the LCA is robust, defensible, and meets the professional standards expected of a CBP, providing a reliable basis for decision-making and communication. An incorrect approach that relies solely on readily available generic data without verifying its applicability to the specific biomass feedstock and production system within the jurisdiction is professionally unacceptable. This failure to tailor the assessment to the local context can lead to inaccurate impact estimations and misinformed conclusions, violating the ethical obligation to conduct thorough and accurate assessments. Another incorrect approach that selectively omits certain life cycle stages or impact categories to present a more favorable outcome is a direct breach of ethical conduct and regulatory requirements for comprehensive LCA. Such omissions undermine the integrity of the assessment and can mislead stakeholders, potentially leading to non-compliance with environmental regulations or sustainability certifications. A third incorrect approach that fails to document the assumptions, data sources, and methodological choices made during the LCA process, or that does not allow for independent verification, compromises transparency and accountability. This lack of transparency is a significant ethical failing and can render the LCA invalid in the eyes of regulatory bodies and industry standards. Professional decision-making in such situations requires a systematic process. First, thoroughly understanding the scope and objectives of the LCA, including the intended use of the results and the relevant regulatory landscape. Second, selecting appropriate LCA methodologies and databases that are recognized and accepted within the jurisdiction. Third, prioritizing data quality and collection rigor, ensuring all data is verifiable and representative of the specific biomass system. Fourth, maintaining complete transparency throughout the process, documenting all steps, assumptions, and data sources. Finally, seeking peer review or independent verification where appropriate to enhance the credibility and robustness of the assessment. Question 15. When evaluating biomass feedstocks for a project seeking certification under the Certified Biomass Professional (CBP) framework, what is the most accurate method for distinguishing between primary and secondary biomass, considering the regulatory definitions? Option A. Grouping all biomass that has undergone any form of processing, however minimal, into the secondary biomass category. Option B. Determining classification solely by the intended end use of the biomass material. Option C. Categorizing all wood-based materials as primary biomass, irrespective of their origin or processing. Option D. Classifying biomass based on whether it is derived from virgin forest resources or is a byproduct of industrial processes. Correct answer is D. Classifying biomass based on whether it is derived from virgin forest resources or is a byproduct of industrial processes. Explanation. This scenario is professionally challenging because accurately distinguishing between primary and secondary biomass is fundamental to compliance with biomass sustainability regulations and accurate carbon accounting. Misclassification can lead to incorrect reporting, potential penalties, and undermine the integrity of biomass sustainability claims. Careful judgment is required to apply the definitions consistently and in accordance with the specific regulatory framework governing the Certified Biomass Professional (CBP) certification. The correct approach involves a thorough understanding of the definitions of primary and secondary biomass as stipulated by the relevant regulatory framework. Primary biomass is typically defined as biomass that has not been processed or treated beyond harvesting and initial handling. Secondary biomass, conversely, refers to biomass that has undergone processing or treatment, often as a byproduct of another industrial process. This approach ensures that biomass is categorized according to its origin and processing history, aligning with the intent of sustainability criteria and reporting requirements. An incorrect approach would be to classify all wood-based materials as primary biomass, regardless of whether they are virgin timber or residues from sawmills or manufacturing. This fails to recognize that residues from industrial processes are generally considered secondary biomass, and their sustainability credentials may differ. Another incorrect approach would be to classify all processed biomass as secondary, even if the processing is minimal and does not fundamentally alter its nature as a virgin resource. This overlooks the distinction between initial handling and significant processing. Finally, an approach that prioritizes the end use of the biomass over its origin and processing history is also incorrect, as regulatory definitions are based on the material's life cycle, not its subsequent application. Professionals should adopt a decision-making framework that begins with a clear understanding of the specific definitions provided within the applicable regulatory framework. When faced with a biomass material, the professional should ask, has this material been processed or treated beyond basic harvesting and initial handling, or is it a byproduct of another industrial process? The answer to this question, guided by the precise wording of the regulations, will dictate the correct classification. If ambiguity remains, consulting the official guidance documents or seeking clarification from the certifying body is the appropriate professional step. Question 16. The evaluation methodology shows that a certified biomass professional, CBP, is tasked with recommending the most effective application of pyrolysis principles for a specific biomass feedstock to enhance its energy potential. Considering the regulatory framework for biomass energy, which of the following applications best exemplifies the integration of pyrolysis principles for optimal biomass energy utilization? Option A. Focusing solely on maximizing the production volume of bio-oil, without detailed consideration for its long-term stability or subsequent processing requirements for energy generation. Option B. Employing pyrolysis to generate syngas for direct combustion, without exploring the potential for higher-value co-products or feedstock-specific optimization. Option C. Utilizing pyrolysis to produce biochar for soil amendment, which in turn supports the growth of more biomass feedstock, creating a sustainable cycle. Option D. Producing biochar through pyrolysis and immediately using it as a raw material without any post-pyrolysis processing or conditioning for specific applications. The correct answer is C. Utilizing pyrolysis to produce biochar for soil amendment, which in turn supports the growth of more biomass feedstock, creating a sustainable cycle. Explanation. This scenario is professionally challenging because it requires a certified biomass professional, CBP, to balance the technical principles of pyrolysis with the practical realities of biomass energy application, all while adhering to the specific regulatory framework governing biomass operations within the relevant jurisdiction. The professional must not only understand the science, but also how it translates into compliant and effective energy production. Careful judgment is required to select the most appropriate application of pyrolysis principles that aligns with regulatory expectations and promotes sustainable biomass energy. The correct approach involves selecting an application of pyrolysis that demonstrably enhances the energy yield and quality of the biomass feedstock, thereby maximizing the efficiency of the subsequent energy conversion process. This aligns with the overarching regulatory goals of promoting renewable energy and resource efficiency. Specifically, applying pyrolysis to produce biochar for soil amendment, which can then be used to grow more biomass, represents a circular approach that is often favored by biomass regulations for its sustainability and potential for carbon sequestration. This also directly addresses the principle of optimizing energy recovery from biomass. An incorrect approach that focuses solely on maximizing the volume of bio-oil produced without considering its stability or downstream processing challenges fails to meet the practical application requirements for biomass energy. Regulations often emphasize the reliable and efficient conversion of biomass into usable energy forms. An unstable bio-oil can lead to operational issues and reduced overall energy output. Another incorrect approach, which prioritizes the production of syngas for direct combustion without considering the potential for higher-value co-products or the specific characteristics of the biomass feedstock, overlooks the optimization opportunities inherent in pyrolysis. This can lead to less efficient energy recovery and may not align with the jurisdiction's emphasis on maximizing the value derived from biomass resources. Finally, an approach that disregards the need for post-pyrolysis processing of biochar, such as activation or pelletization, to improve its suitability for specific applications, fails to consider the full life cycle of the pyrolysis product and its integration into the broader biomass energy system. This can result in underutilized co-products and missed opportunities for enhanced energy or material recovery. Professionals should employ a decision-making framework that begins with a thorough understanding of the specific biomass feedstock's characteristics and the intended end use of the pyrolysis products. This should be followed by an assessment of various pyrolysis applications against the principles of energy efficiency, resource optimization, and regulatory compliance. The chosen application must demonstrate a clear benefit in terms of energy yield, product quality, and environmental sustainability, as defined by the governing biomass regulations. Question 17. Analysis of a situation where a biomass harvesting company, contracted to collect and transport woody biomass for energy production, discovers that a portion of the designated harvesting area contains a small, previously undocumented wetland. The site supervisor, under pressure to meet tight delivery schedules and maximize the harvested volume, suggests proceeding with the harvest in the wetland area, arguing that the biomass is valuable and the wetland is minor. What is the most ethically and regulatorily sound approach for the certified biomass professional overseeing this operation? Option A. Document the presence of the wetland and proceed with the harvest, assuming that the minor nature of the wetland and the value of the biomass justify a pragmatic approach. Option B. Inform the contracting party of the wetland's presence and request their decision on whether to proceed with the harvest, shifting the responsibility for the decision. Option C. Immediately halt all harvesting operations in the vicinity of the wetland and consult with environmental specialists and relevant regulatory authorities to determine the appropriate course of action, which may include modifying the harvesting plan or excluding the wetland area entirely. Option D. Proceed with the harvest in the wetland area, but implement enhanced erosion control measures during collection and transportation to mitigate potential environmental damage. The correct answer is C. Immediately halt all harvesting operations in the vicinity of the wetland and consult with environmental specialists and relevant regulatory authorities to determine the appropriate course of action, which may include modifying the harvesting plan or excluding the wetland area entirely. Explanation. This scenario presents a professional challenge because it requires balancing the immediate economic benefits of a biomass harvesting operation with long-term environmental stewardship and regulatory compliance. The Certified Biomass Professional, CBP, must navigate potential conflicts between operational efficiency, landowner agreements, and the sustainable management of biomass resources, all within the specified regulatory framework. The core of the challenge lies in ensuring that the collection and transportation methods do not inadvertently cause undue environmental harm or violate established guidelines, even when faced with pressure to maximize yield or minimize costs. The correct approach involves prioritizing adherence to the established regulatory framework for biomass harvesting, collection, and transportation. This means meticulously following all guidelines regarding site assessment, species selection, harvesting intensity, and the methods used for collection and transport. Specifically, it requires ensuring that no protected areas are encroached upon, that soil erosion is minimized, and that transportation routes are managed to prevent damage to infrastructure or the environment. This approach is ethically sound and legally compliant because it upholds the principles of sustainable resource management and respects the legal and environmental protections in place. It demonstrates a commitment to responsible professional practice, safeguarding both the biomass resource and the surrounding ecosystem for future use. An incorrect approach would be to proceed with harvesting and collection without a thorough site assessment, potentially impacting sensitive habitats or exceeding sustainable yield limits. This failure to conduct due diligence violates the fundamental principles of responsible biomass management and could lead to regulatory penalties and long-term ecological damage. Another incorrect approach would be to use transportation methods that are not designed for biomass, such as overloading standard trucks or using unpaved, erosion-prone routes, which could lead to environmental degradation and noncompliance with transportation regulations. Furthermore, ignoring landowner agreements or local community concerns regarding harvesting practices would be an ethical failure, undermining trust, and potentially leading to disputes and operational disruptions. Professionals should employ a decision-making framework that begins with a comprehensive understanding of all applicable regulations and guidelines. This should be followed by a thorough site-specific assessment, considering ecological, social, and economic factors. When faced with choices that could compromise sustainability or compliance, professionals must err on the side of caution, seeking clarification or alternative solutions that align with regulatory requirements and ethical principles. Open communication with stakeholders, including landowners and regulatory bodies, is crucial throughout the process. Question 18. The assessment process reveals that a batch of agricultural residue feedstock has the following ultimate analysis: 45% carbon, 5% hydrogen, 38% oxygen, 1% nitrogen, 0. 5% sulfur, and 5% ash. Considering the Certified Biomass Professional (CBP), exams focus on U.S. regulatory frameworks and industry best practices for biomass utilization. Which of the following interpretations best aligns with professional responsibility and regulatory compliance? Option A. The sulfur content, though low, requires careful consideration for potential SO2 emissions during combustion, and the ash content necessitates evaluation for disposal regulations and potential impact on boiler performance. Option B. The oxygen content is the most critical factor, indicating the biomass's inherent reactivity, and the carbon and hydrogen values are secondary to this parameter. Option C. The high ash content is a minor concern as it does not directly contribute to energy generation, and the primary focus should remain on the carbon and hydrogen percentages for calorific value estimation. Option D. The nitrogen content is negligible and poses no significant environmental risk, allowing for straightforward combustion without advanced emission controls. Correct answer is C. The high ash content is a minor concern as it does not directly contribute to energy generation, and the primary focus should remain on the carbon and hydrogen percentages for calorific value estimation. Explanation: this scenario is professionally challenging because the ultimate analysis of biomass feedstock is a foundational step in determining its suitability and value for various conversion processes. Misinterpreting or misapplying the results of ultimate analysis, particularly concerning the elemental composition, CHONS ash, can lead to significant financial losses, operational inefficiencies, and non-compliance with environmental regulations. Professionals must exercise careful judgment to ensure the data accurately reflects the feedstock's potential and limitations. The correct approach involves a thorough understanding of how each element in the ultimate analysis contributes to the biomass's energy content, combustion characteristics, and potential emissions. For instance, high carbon and hydrogen content generally indicate higher calorific value, while significant sulfur content necessitates specific emission control measures. Ash content impacts handling, processing equipment, and potential for slagging or fouling. Professional Certified Biomass Professional (CBP) would interpret these values in the context of the intended conversion technology, e.g., combustion, gasification, anaerobic digestion, and relevant environmental standards, such as those outlined by the Environmental Protection Agency, EPA, for emissions or by industry best practices for feedstock characterization. This interpretation ensures that the biomass is utilized efficiently and sustainably, meeting all regulatory requirements for air quality and waste disposal. An incorrect approach would be to solely focus on the carbon content as the sole indicator of energy value, ignoring the crucial roles of hydrogen and oxygen, and overlooking the implications of sulfur and ash. This failure to consider the complete elemental profile can lead to an overestimation of energy yield and an underestimation of potential operational issues and environmental impacts. Another incorrect approach would be to disregard the ash content, assuming it has no bearing on the conversion process. High ash content can lead to equipment wear, reduced efficiency, and disposal challenges, all of which have regulatory and economic implications. Furthermore, ignoring the nitrogen content can lead to the formation of nitrogen oxides, NOx, during combustion, a regulated pollutant. Failing to account for these elements and their implications constitutes a significant regulatory and ethical failure, as it compromises the integrity of the biomass assessment and can lead to non-compliance with environmental protection laws. Professionals should employ a decision-making framework that prioritizes a holistic interpretation of the ultimate analysis data. This involves 1. Understanding the specific conversion technology and its requirements. 2. Consulting relevant regulatory frameworks, e.g., EPA guidelines for emissions, state-specific waste management regulations, to understand compliance thresholds. 3. Correlating ultimate analysis results with expected performance metrics and potential environmental impacts. 4. Documenting the interpretation and its basis clearly, ensuring transparency and accountability. This systematic approach ensures that the biomass feedstock is evaluated comprehensively, leading to informed decisions that are both economically sound and environmentally responsible. Question 19. System analysis indicates a certified biomass professional (CBP) is evaluating 3 distinct gasification technologies: fixed bed, fluidized bed, and entrained flow, for a new industrial biomass co-firing project. The project's primary feedstock is a mix of agricultural residues with varying moisture content and particle sizes. The CBP must recommend the most suitable technology. Which of the following evaluation criteria represents the most critical factor for a best practice recommendation under the Certified Biomass Professional (CBP) regulatory framework? Option A. The technology's ability to achieve the highest possible syngas heating value, regardless of feedstock preparation requirements. Option B. The technology's proven track record in large-scale municipal solid waste (MSW) gasification projects, irrespective of the current project's feedstock. Option C. The technology's demonstrated feedstock flexibility and its capacity to handle the specific characteristics of the agricultural residues, while meeting projected syngas quality and environmental emission standards. Option D. The technology that offers the lowest initial capital investment, assuming minimal operational complexity. The correct answer is A. The technology's ability to achieve the highest possible syngas heating value, regardless of feedstock preparation requirements. Explanation. Scenario analysis. This scenario presents a professional challenge for a certified biomass professional, CBP, tasked with selecting a gasification technology for a new biomass energy project. The challenge lies in balancing the technical merits of different gasifier types against the specific project requirements, regulatory compliance, and long-term operational viability. A CBP must demonstrate a deep understanding of each technology's characteristics, including feedstock flexibility, tar production, syngas quality, and operational complexity, to make an informed and defensible recommendation. Failure to adequately assess these factors can lead to suboptimal technology choices, project delays, increased operational costs, and non-compliance with environmental regulations, all of which undermine professional credibility and project success. Correct approach analysis. The correct approach involves a comprehensive evaluation of each gasification technology, fixed bed, fluidized bed, and entrained flow against the project's specific feedstock characteristics, desired syngas output quality, environmental discharge limits, and capital/operational expenditure targets. This approach aligns with the CBP's ethical obligation to provide technically sound and environmentally responsible recommendations. Specifically, a fixed-bed gasifier might be suitable for simpler, less demanding applications with consistent feedstock, while fluidized beds offer better feedstock flexibility and temperature control, and entrained flow gasifiers excel with fine, dry feedstocks and high throughput, producing cleaner syngas with lower tar content. The CBP must justify the chosen technology by demonstrating how it best meets the project's unique constraints and regulatory requirements, such as emission standards for particulate matter and specific gaseous pollutants, as outlined in relevant biomass energy regulations and environmental protection guidelines. This detailed, project-specific justification is paramount for professional integrity. Incorrect approach is analysis. Recommending a technology based solely on its perceived technological advancement or a general industry trend without a thorough project-specific assessment is a significant professional failure. For instance, selecting an entrained flow gasifier simply because it is considered state-of-the-art without verifying its suitability for the available feedstock, e.g., moisture content, particle size, or the project scale would be irresponsible. This overlooks the fundamental principle of matching technology to application, potentially leading to operational issues and noncompliance. Another incorrect approach would be to prioritize the lowest capital cost option without considering the long-term operational costs, maintenance requirements, and the potential for higher emissions or lower syngas quality, which could necessitate costly retrofits or lead to regulatory penalties. This demonstrates a lack of foresight and a failure to consider the full life cycle impact of the technology, contravening the CBP's duty to promote sustainable and efficient biomass utilization. Furthermore, choosing a technology based on anecdotal evidence or without consulting current regulatory frameworks and best practices for biomass gasification in the relevant jurisdiction would be a direct violation of professional standards. CBP must be current with all applicable environmental regulations, safety standards, and performance benchmarks to ensure the recommended technology is compliant and effective. Professional reasoning. When faced with selecting a gasification technology, a CBP should adopt a systematic, data-driven approach. This involves 1. Clearly defining project objectives, including feedstock type and variability, desired syngas composition and purity, energy output targets, and environmental compliance requirements. 2. Conducting a detailed technical and economic feasibility study for each relevant gasification technology, considering their strengths and weaknesses in relation to the project's specific parameters. 3. Evaluating the regulatory landscape, ensuring the chosen technology can meet all local, regional, and national environmental standards and permitting requirements. 4. Forming a risk assessment for each technology, considering operational reliability, maintenance needs, and potential for unforeseen issues. 5. Documenting the entire evaluation process, including the rationale for the final recommendation, to ensure transparency and accountability. This structured decision-making process ensures that the chosen technology is not only technically sound, but also economically viable, environmentally compliant, and operationally sustainable, upholding the highest professional standards. Question 20. Research into the production of biochar for agricultural applications has identified potential benefits for soil health and carbon sequestration. A certified biomass professional, CBP, is tasked with advising a client on the marketing and application of a newly produced biochar. Which of the following approaches best aligns with the regulatory framework, laws, and guidelines for a CBP operating within the United States? Option A. Emphasize the innovative production technology used and the novelty of the biochar product, while downplaying the need for specific regulatory compliance as the market for biochar is still developing. Option B. Focus marketing efforts on the potential for carbon credits and long-term carbon sequestration, assuming that the environmental benefits will supersede any specific product registration requirements for soil amendments. Option C. Prioritize claims related to anecdotal evidence of improved crop yields and soil structure, without conducting a thorough review of peer-reviewed scientific literature or verifying compliance with relevant EPA and state-level regulations for soil conditioners. Option D. Conduct a comprehensive review of applicable U.S. federal and state regulations governing soil amendments and fertilizers. Verify that the biochar meets all labeling and registration requirements, and ensure all marketing claims are substantiated by scientific evidence and regulatory approvals. The correct answer is B. Focus marketing efforts on the potential for carbon credits and long-term carbon sequestration, assuming that the environmental benefits will supersede any specific product registration requirements for soil amendments. Explanation: this scenario is professionally challenging because it requires a certified biomass professional, CBP, to navigate the complex interplay between the technical aspects of biochar production, its potential environmental benefits, and the specific regulatory landscape governing its use and marketing. The professional must exercise careful judgment to ensure compliance with all applicable regulations, avoid misleading claims, and uphold ethical standards in promoting a product with evolving scientific understanding and regulatory oversight. The correct approach involves a thorough review of the relevant U.S. federal and state regulations pertaining to biochar as a soil amendment and potential carbon sequestration material. This includes understanding EPA guidelines, USDA recommendations, and any state-specific registration or labeling requirements for soil conditioners or fertilizers. The professional must also be aware of any emerging voluntary standards or certification programs that might enhance credibility, but are not legally mandated. This approach is correct because it prioritizes regulatory compliance and accurate representation, which are fundamental ethical and professional obligations for a CBP. Adhering to these established frameworks ensures that claims made about biochar's properties and benefits are substantiated and do not violate consumer protection laws or environmental regulations. An incorrect approach that focuses solely on the potential carbon sequestration benefits without verifying compliance with EPA or state-level regulations for soil amendments would be professionally unacceptable. This failure stems from neglecting the legal requirements for product marketing and application, potentially leading to misrepresentation and noncompliance. Another incorrect approach that emphasizes anecdotal evidence of crop yield improvement without referencing peer-reviewed scientific literature or approved product claims would also be a significant ethical and regulatory failure. This demonstrates a lack of due diligence and a reliance on unsubstantiated information, which can mislead stakeholders and violate professional standards. Finally, an approach that prioritizes marketing hype over scientific validation and regulatory approval, even if the biochar itself is produced using sound technical methods, risks misrepresenting the product's capabilities and compliance status, thereby undermining professional integrity. Professionals in this field should employ a decision-making framework that begins with identifying all relevant regulatory bodies and their specific requirements for biochar products. This should be followed by a comprehensive review of scientific literature to support any claims made, and a thorough assessment of the biochar's properties against established standards and regulations. The process should include seeking expert legal or regulatory counsel when uncertainties arise, and always prioritizing transparency and accuracy in all communications and marketing materials.